last time we did some beginning look at continuity or continuous functions, and we need to do a few more examples of this today. A few examples dealing with something called piecewise functions. We haven't gotten to this level yet. And so the first example I want to look at is, so I'm going to pick one out of the book here. F of x equals x minus 1 when x is less than 1. It is equal to 0 if x is between 1 and 4. And it's equal to x minus 2 if x is greater than 4. Right. In algebra, you worked with graphing these types of equations, and you also looked at evaluating y-coordinates on these types of equations. Okay. What we want to do today is something similar to that, except we want to look to see, is the graph continuous? Or does it have jumps when we change from one equation to the next? Okay. So first thing we'll do, let's draw a picture of this. Let's graph it, because then it will look a lot like the problems that we did last time. Okay, on a piecewise function, what we try to do is we try to graph this equation, but instead of graphing the entire line, since this is a linear equation, instead of graphing the whole thing, we only graph the line until we get up to 1, and then we stop the graph. So it's just a piece of the graph, hence the name piecewise function. Okay? So we know this graph has a y-intercept of -1, and it has a slope of 1. It's just a linear equation. So if I was to graph the whole thing, now you may not want to draw this yet, but if I was to graph the whole thing, it would look something like this. Now, I only want a piece of this function. I only want the part of the graph when x is less than 1. So what I need to do is come in here and erase all the graph after x equals 1. Now, one of the key questions will be, well, where's the y value at x equals 1? You know, is it right at 0? Is it above the x-axis? Is it below the x-axis? Well, how would we get that? All we do is we just take 1 and sub it into this equation. What do I get when I sub in 1? I get 0. So that tells me that this graph, or that this critical point where the graph stops, is right here at 1, 0. Okay? Now, for right now, I probably should have done it this way. For right now, this should probably be an open circle. Since we don't actually get to the value x equals 1, I probably need to have it open for right now. Now, we may end up closing it here in a minute, but okay. All right, the second graph that I want to graph is y equals 0. Y equals 0 is just a horizontal line at a height of 0. So in other words, it's right along the x-axis. But again, I don't want the whole line. I only want the part of the line from 1 to 4. So in other words, I just want a segment from x equals 1 to x equals 4. Okay? Well, x equals 1 happens to match up with this point, doesn't it? So I start the graph right here, and I continue the graph over until I get to x equals 4, and I'll stop it right there. This time I filled in the circle because it's x less than or equal to 4. So I want to actually get to that point. All right, the last graph that I need to do is y equals x minus 2. This is, again, a linear equation, slope of 1, y-intercept of 2. Okay? So again, I could plot the whole graph. I could start at the y-intercept, graph it, and go from there, but I really don't need the whole graph. Excuse me. The only part that I need is the part after x equals 4. So I think the best thing to do here is actually plug in 4 and see where this graph should start. If I sub in 4 here, I get what? 2. So I'm going to start this graph at 4, 2, at a height of 2. Now, from here, I know that my slope is 1. This one had a slope of 1, so those lines should be parallel to each other. And so I can rough sketch my picture, trying to make those lines look like they're parallel. Okay? And this is good enough. I mean, we just need a rough idea of what this looks like. Because now we can answer all that continuity. First of all, where the first equation meets the second equation, is this considered continuous? From our discussion the other day, can I draw this whole thing without picking up my pencil? Yes. So far I am continuous, but then as soon as I get over here to x equals 4, can I now draw the rest of this graph? No. I have to pick up my pencil to do that, So there it is therefore discontinuous at x equals 4. Okay? Just to ask some follow-up questions for a little bit of a review, what would be the answer to this question? Limit as x approaches 4 from the left side is equal to what? Remember what limit means. Limit just means y value. So the y value as x approaches 4 from the left side is what? It is 0. The y value, as I get closer and closer to x equals 4, that y value is 0, isn't it? So that's my limit. That's what limit means, just a y value. Okay, what about the other side? What is the limit as x goes to 4 from the right side on this function? In other words, what is the y value as x approaches 4 from this direction? Y value is 2. Exactly. That's what we just calculated a little bit ago. Okay? Therefore, this makes it really easy to tell, since one side's limit is 0, the other side's limit is 2, okay, definitely I can tell there is a jump in this function. Okay? So yeah, we've answered those limiting questions as well. All right, questions with that? This is one type of problem you'll see on your homework. Another type of problem dealing with piecewise functions will be one like this. What if we've got g of x, and the first equation is x cubed plus some other number k if x is less than or equal to 3, and it is kx minus 5 if x is greater than 3. Now, this type of question wants us to go in and find out what number could we substitute in here for k so that we would have a continuous function. Okay? So over here, we're trying to make a situation like this, where the first equation meets the second equation at the same point. Right? Now, it's going to be a little harder to do this graphically because we don't know what these values are, and of course that will affect our equation quite a bit. But what's the key thing that we're trying to accomplish over here? When these graphs meet up with each other, what does that mean is true about this location right here? What's the same about this point on the first equation and on the second equation? Think back to this right here. Limit is your what? What's another name for limit? Y value. So what's the same about the y value on this equation and the y value on this equation at this point? They are the same, aren't they? They have to have the same y value, and that makes sense. If we want two graphs to meet up with each other, they've got to have the same y value. Okay? Now, how do we ensure that they have the same y value? Well, what we want to do is we want to take this equation and we need to set it equal to the second equation. We want the equations to match up or to have the same y value. Okay? So I take x cubed plus k equals kx minus 5. I need these equations to have the same y value, so I set them equal to each other. Now, the other thing that's the same on both of these, yes, they have the same y value, but what else is the same over here? What other value is the same? Okay, they both have the same x value, and in this case, they had the same value of x equals 1. What x value are we concerned about on our example? We are caring about what happens at x equals 3 because that's where we change from one equation to the next. So therefore, I can go ahead and substitute in 3 for all of my x's because that's the one x coordinate that I care about. All right, so if I plug in 3 here, let's see, 3k minus 5 over here. Now I just have a linear equation to solve, and the value that I get for k will be the appropriate one to ensure that both the x values are the same as well as the y values. Okay? Just the algebra to finish this off here. If I subtract k from both sides, I will have 2k left on the right side. If I add 5 to both sides, I will have a 32 over here. Divide both sides by 2. Looks like the k value that I need for this particular problem is 16. Okay? So if you were to go to your calculator and you were to graph x cubed plus 16, and you were to graph 16x minus 5 and just look where those graphs intersected or met each other, they should meet each other at 3 because that's where the one graph would stop and the other one would start. Okay? All right, so any questions with that type of problem? So a couple of things we can do with piecewise functions in terms of continuous functions or continuity. All right. The next major concept we want to look at as we start working toward this first major calculus concept of derivative. We're going to look at graphs of equations and graphs of slope equations. Okay? So now we're going to switch gears a little bit, and this is not the easiest thing to pick up on. Okay? So I want to spend a little bit of time on it here. Let's start out with a pretty basic example. Let's start out with the graph of y equals x squared, okay? Because we all know what this graph looks like. And if you have your calculators, you may want to take those out as well. We can, because we're going to do some work on those. Okay? If you would type in the equation x squared, let's see, x squared. We all know that this is just a parabola that's got a vertex at the origin here. Now, our goal in this section is that if we are given a function, x squared, we want to be able to draw what is called the slope function of this graph. Okay? So this is the original function. We now want to be able to graph all of the points' slopes, because this will, again, lead us into this concept of a derivative later on. Okay? For right now, let me just give you a little bit of a way to let the calculator do some of this figuring for us. Okay? If you go to second calculate, one of the options, we've done some work with number 1 with values. If you look down, there's a number 6, dy dx. And what this is standing for the change or the difference in the y-coordinates divided by the difference in the x-coordinates. Okay? And that's how we find slope, isn't it? We look at how much the y changes, we look at how much the x changes, and we divide them. So number 6 finds slope values for us, and that's what I want us to do. So go ahead and choose number 6. And the next thing that it's waiting for is it's waiting for us to input a value. Where do we want to find the slope? Okay? All right, so let me make a little table here. On the left side, we'll list some x values. On the right side, we will list some values for slope. Okay? And I'm going to start here in the middle, but let's start with x equals 0, because I think this is the easiest one to see. So go ahead and type in 0, push enter, and what is our slope at 0? Slope at 0 is 0. Okay, now, the reason I say this is the easiest one to see, if I was to come into this graph here, and if I was to pick this point right at the origin, if I wanted to draw something called a tangent line. A tangent line is a line that touches this graph in only one point. So I want to come along and I want to draw a line that will touch this graph in only one point, and I want to see what is the slope of that line. Can you see that this line would have to be a horizontal line? If I want to just hit the bottom point, that vertex, that's going to have to be a horizontal line, so therefore its slope is 0. Okay? So I think that's the easiest one to see. Now, what if I come over here to x equals 1? Okay, we'll do it on the calculator here in just a second, but just roughly let's look at what we think the tangent line would look like. Okay, what direction will the tangent line be going if I draw it for x equals 1? Okay? Won't it be some type of an increasing line? Won't it be something that looks roughly like this? Okay? And so I should know, or I should notice, that the slope of this point will be a positive number. Okay? I don't know what it is. It might be 1, it might be 2, it might be 5, but I recognize that it's a positive number. Okay? Now, what if I come over here to x equals 2? Okay? And again, if I draw the tangent line, A little crooked there. Okay. Again, I recognize it's a positive number, but if this one happens to be a slope of 5, what do I know about the slope of this one? Is it smaller than 5 or bigger than 5? Is the steepness smaller or is the steepness bigger? The steepness is bigger, right? So if this one, and again, I'm just guessing here, if this one had a slope of 5, this one might have a slope of 10 or 15, we recognize that it's a bigger value. So what it appears is happening is that as the x's get larger, what is happening to the steepness of those tangent lines? They're getting larger and larger, aren't they? So as x is going up, this y value is going up. Okay, or not the y value, but the slope value is going up. Now, let's go ahead and actually find out what those numbers are. So go ahead and do your dy dx for 1 and 2, and then let's go ahead and do 3 as well. And then tell me what those values are. What is the slope at 1? 2, okay. What is the slope at 2? 4. And the slope at 3? Shouldn't be 9. 6. Should be 6. Okay. Check it again. Yeah, at x equals 3. Make sure, now be careful, make sure that you get on your answer, make sure you get a dy dx equals and not just the actual xy ordered pair. Okay? You have to always go back in and do second calculate dy dx or else it just gives you a value. Okay, all right, good. All right, now let's do the same thing on the other side here. Okay, what if we go back the other direction? Now, even before we do this, let's just think about it. We probably don't even have to type this in the calculator. If the slope at 1 happens to be 2, what do we think the slope will probably be on this side? Probably negative 2, right? Because we got some nice symmetry on this graph. And if you check it, is that what you get? And the answer is yes. All right, so the slope here is negative 2. Therefore, what's the slope for this one? Negative 4 and negative 6. Sure. All right. So we've come up with a nice table of values describing x and describing the slope. Now I want to graph these values. Okay, so let's come over here and remind ourselves that we are graphing x on this axis and we are graphing slopes on this axis. So this is a different type of graph. That's why it's a little confusing. We're just used to always looking at x and y coordinates. Now we're looking at x's and slopes. Okay? All right, if I start plotting some of these points, negative 3, negative 6 down here, negative 2, negative 4, negative 1, negative 2, 0, 0, 1, 2. Okay? What type of picture am I starting to develop? It's definitely a linear picture, right? Definitely looks like a line. How can I be sure that this is going to be a line just by looking at these y coordinates? Or these slope coordinates, I guess. What's the common difference in all these? I have a common difference of 2, and that's what a linear equation looks like. You have a common difference all the way through here. Okay? All right, now my next goal or next thing that I would like for you to try to figure out, can we write the equation of this line? And I think we should be able to. What are the two things we need to write an equation? We need a slope and we need a y-intercept. Okay? Those are the two values. Now, we could look at a slope and just a different x value, but I think we'll go ahead and look at mx plus b right here. We'll go ahead and look at slope and y-intercept because what is my y-intercept here? It's 0, isn't it? Since we have that number, that we'll just go ahead and use it. Okay, so this is 0. What is my slope on this graph? If I try to get from one point up to the next point, how much do I change vertically and how much do I change horizontally? I change vertically by 2 and horizontally by 1. Right. You know, my change in y is 2. My change over here is in x is 1. So 2 divided by 1, so therefore my slope is 2. So the equation of this line is y equals 2x. Now, the big advantage of this is that if I want to know on this graph what is the slope at x equals 100, I don't necessarily have to go back and do a lot of work on here. I can just go straight over to this equation and see that the slope will be equal to what? 200, exactly. If I sub in 100 here, this is my slope equation. My slope equation tells me that the slope will be 200. Okay? So that's why we want to write these equations for slope. Okay? All right, any questions with this example? Now, this one was nice because we had a function, x squared. We could plug it in our calculator and find a nice table of values with slope. A lot of the questions in this section of the book will not have an equation for us. We're just going to try to rough sketch out a picture like this just by looking at what we think the slopes are at those points. So it's going to be a little bit of a guessing game. Your answers might vary a little bit, but there are some things that you should recognize. Okay? And so let's look at some examples where we don't have the equation, and we just try to rough sketch out a picture. Okay? All right. First example I'm going to do is this one. All right, it looks like negative 2, 2 is an important point. Then it will go down to the origin. Then it will come up to 1, 1, and then go off to the right. Okay? So we've got some type of a piecewise function here. Okay, but we don't have the equation. Okay? We want to try to draw the graph. This is just x and y. We want to try to draw the graph of x versus the slope and see what this looks like. Okay. All right, well, let's start thinking about this. Okay, I'm going to go ahead and mark negative 2, or think about negative 2 as a critical point, because that's where I change from one graph to the next. Okay, let's start everything to the left of negative 2. Okay, if I pick this point, or this point, or this point, what is the slope at any one of those points? Since it's a straight line going across, what's the slope? Slope is 0, isn't it? The slope of any horizontal line is always 0. So on my graph down here, I need to graph a whole bunch of zeros until I get to that point, because the graph is up here, but the slopes are all 0. Okay? Now, I'm going to jump to the other side of the graph. What happens when I get to x equals 1? What happens with all these points over here? What are their slopes? The slope of that line is also 0, isn't it? Okay? So again, on my graph, I will have a whole bunch of zeros once I get past x equals 1. This graph and this graph have the same slope. They both have a slope of 0. So that's why I plotted a whole bunch of zeros along there. Okay? Now, let's look at this little V shape here in the middle. Okay? If I look at this linear equation, this is a straight line here, what is the slope of that line? Okay, we're going to get from this point to this point, we need to go down 2 units and to the right 2 units. So negative 2 divided by 2 is negative 1. So the slope of that line has to be negative 1. So all the way from negative 2 to 0, so from negative 2 to 0, I need to be graphing things at a slope value of negative 1, because that's what the slope is the entire time. The slope is always negative 1. Okay? All right, now I come over here and I look at the other side of this V shape. What is the slope of that line? Slope is 1, right? Because I go up 1 and to the right 1. So therefore, I need to graph from 0 to 1, I need to graph a slope of 1. Okay? And this is the graph of what we're going to call here in a little bit, we're going to call this the derivative. Okay? This is the graph of the derivative of this original function here. Okay? All we're doing is we're looking for the slopes at each one of those locations, and we're plotting those points. Okay? And in this particular case, since we had a whole bunch of just nice straight lines, we ended up with a whole bunch of nice lines down here. Okay? So I wanted to pick that example first. Okay with that? I mean, that's, again, it's a different way of thinking. You've probably never had to graph slopes before, and so that's what makes it hard. Okay? Let's pick another example here. Okay. And let me put it up a little higher so I can draw the other one right below it. Okay, so what if we look at this example? Negative 6 starts here at 0. Then it goes up and comes back down through negative 3. Then it goes down and comes back through 0. And then up and back down through x equals 3. And then pretty far down before it comes back up here at x equals 6. Okay, so we just get kind of a wavy function here. Okay, what will the graph of this one's slope look like? Let's center it right below it here. Okay. This one's a little more difficult to work with, but I think we can do some things. We can figure out some things right away. The first thing that I would look for on this graph, if I was trying to graph its x versus slope picture, I would look for, are there any places where the slope is equal to 0? Is there anywhere on this graph where I have a tangent line, if I drew that tangent line, that the slope would be 0? And there's a whole bunch of places. Does anybody recognize one of them? Where was the slope 0 on this graph over here? Right at one of the peaks or one of the valleys, right. Okay, on this example, the slope was 0 right at 0 because my tangent line was straight across. It was horizontal. Okay, so over here on this graph, right at this peak, my tangent line will have a slope of 0. Okay, so when I draw my graph down here, and we'll just assume that that's right in the middle. We'll assume that's negative 4.5. So on negative 4.5, I need to have a slope value of 0. And so I just put a dot there for right now. Where else do I need to have slopes of 0? Okay. Negative 1.5 should have a slope of 0 because it'll be a valley. Where else do I need a slope of 0? Positive 1.5 and... Okay, probably over here about 4.5 somewhere. Yeah. 3, 4, 5, yeah. Okay, so that's the first thing I try to pick out. Any places where the slope is equal to 0. And like we just said, it's peaks and valleys is what it is. Okay? All right, now, what we've got to decide is what is happening between the negative 6 and this first peak right here. What is happening to my slopes? Okay? All right, let me get a different color out here. See if this will be easier to notice. First of all, if I just pick a point a little bit to the right of negative 6, what type of value is that slope? Positive or negative? Definitely positive, right? And the line is increasing, so it is definitely positive. Okay? I don't know what its value is. I don't know if it's 2 or 4 or 6, but I know it's positive. Okay. What happens, though, as I go a little bit farther to the right? What happens to that slope? Is it still positive? Yes. Is it as positive as it was a little bit ago? Or is it as large as it was a little bit ago? No. If this one, again, I'm just making up numbers, if this would be a slope of 5, this would have to be something smaller than 5 because it is not as steep. Okay? Now, what's happening to these slopes? Well, maybe this one was 5, the next one was 4, then 3, then 2, then 1, and then it gets to the peak and it has a slope of 0. So what happens on my graph here is over here at negative 6, I start out with a slope up here. And you don't really have to label the values here because we don't really know what those numbers are. We don't know if it's 5 or we don't know if it's 10, but we just know it's positive. But what's happening to the values of those slopes before I get to this point? They're decreasing. Aren't they getting smaller and smaller? So aren't the values, like if this was 5, then it was 4, then it was 3, then 2, then 1, and now it's down to 0, isn't it? So again, we don't have to have perfect graphs, but just a rough sketch that you should know that the slopes are decreasing. Okay, now, what's happening from here over to here? Okay, all right, well, if I just look a little bit to the right of that point, what would you do for the tangent line? Is it positive or is it negative? Definitely negative. Okay, so the tangent line here might be negative 10, or probably not that much, probably negative 2. Okay, but what happens if I go a little farther to the right? If the first one was negative 2, the second one might be what? Maybe negative 4 or negative 5 or something, right? It's a little, it's steeper, so it's got a bigger value attached to it. Okay, so I started out with some slope values around negative 2. Now I'm getting down to -5. So my slopes are getting smaller and smaller, aren't they? Okay? Let's keep going along here. What happens though once I get to this point? Well, I've got a pretty steep slope for negative, but what starts to happen to my slopes as I get closer to this valley? Okay? If this slope was really steep at -5, what starts to happen as I walk along this graph? The slopes start to get closer and closer to 0 again, don't they? Okay? So what happens is somewhere here in the middle, I hit a low point, and then my slopes start coming back and getting closer and closer to 0. Okay? So I had, for the first part of the graph, it was getting steeper and steeper. Now it's starting to level back out again. And so that's what's happening on this piece. Okay? All right, let's keep going here. What about if we go past this point? Well, my slopes are what? They're positive, and what's happening to their values? They're getting bigger and bigger, aren't they? But then eventually, somewhere in between these 2 points, what starts to happen again? They start to level back off to 0, don't they? So the slopes get bigger and bigger, but eventually they start to level back off to 0 again. Okay? And you can kind of guess from here what's going to happen. We're going to get the same thing, right? We're just going to keep getting these waves. We start out with really negative slopes, but then eventually they start to level back off again. So negative slopes, they level back off. And then finally what happens once I get past 4.5? I get a whole bunch of positive slopes from there. Okay? And so this is a really rough sketch. Now, what the things I will be looking for, on a test question, when I give you a graph of this and I ask you to rough sketch a picture of this, I won't be looking for an exact drawing compared to mine. I will look for these things though. You should be able to identify all the points where the slope is 0. Okay? So that's one thing that you should definitely be able to pick out. The other thing that I will care about is that, do you have your graph on the right side of this line? Do you have the positive slopes where they're supposed to be? Do you have the negative slopes where they're supposed to be? Okay? I don't really care if this graph looks like this or if it looks like this. As long as you've got positive and negative slopes in the correct location, that's all I really care about. So your graphs can be pretty rough and still get the idea across to me. Okay? All right. We'll continue with this next time as well.